Alright, I'm going to do a bunch of problems from section 11.1, starting with number 23. So in this section here, in 23 through 56, this is the main thing you need to learn from this section, is when you have a sequence, you're just asked to take the limit and find out whether it converges or diverges in the same way that you were asked to take limits in Math 2A. So for this one here, the key to recognize, they want you to see the 0.2 to the n power. They expect you to know this fact, that the limit as n goes to infinity of r to the n equals 0, as long as r is less than 1, the absolute value of r is less than 1, and r is just a fraction here. So 0.2 counts as a fraction. So when I do the limit as n goes to infinity of 1 minus 0.2 to the n, this part here goes to 0, so the limit equals 1. And so the an converges to 1. That's the language we use for that. Okay, number 26. This is from your assigned work. Number 26 is an equals n cubed over n plus 1. I'm going to do the same thing. Here, you're supposed to recognize that the power on the top is bigger than the power on the bottom, and so this is going to go to infinity in the same way that in Math 2A, if you have a limit as x goes to infinity of x cubed over x plus 1, you're expected to realize that, oh, the x cubed dominates, so this goes to positive infinity. We say it diverges. Same thing for this. The limit as n goes to infinity, n cubed over n plus 1. If you like, you can say this is equal to infinity over infinity, and you can use L'Hopital's rule if you want. This is another way to do this if you're just not confident in just looking at the exponents. So that's 3n squared over 1, and that equals infinity. So we say this diverges. A and diverges. Number 27 is an equals e to the 1 over n. So a lot of times they'll just put a regular sequence and put it in an exponent of e or in a logarithm or something like that. So what you want to do when you're looking at this is to just focus on the 1 over n. And 1 over n, we know this, the limit as n goes to infinity of 1 over n, that's equal to 0. So this is equal to e to the 0, which is 1. So it converges. So a n converges. 28. This isn't assigned. This isn't one of the assignments, but this is a good one to go over because this is the kind of thing that if you get it on a test, it's kind of confusing because it's got some exponents, and if you haven't practiced them ahead of time, they can be a little tricky. Okay, so the way I think of this is I'm keeping in the back of my mind, if I have a fraction to a power, like 3/5, for instance, that's something I can deal with. This goes to 0. So what I want to do since I can get a handle on this, what I want to do is I want to turn this into the 3/5 to the n. So what I'm going to do is I'm going to factor out, I'm going to rewrite this as 3 squared 3 to the n over 5 to the n, and then that is equal to 9 times 3/5 to the n. So the limit as n goes to infinity of 9 times 3/5 to the n, well, this part here goes to 0 simply because I have r to the n. R to the n goes to 0 if r is less than 1. So if r is a fraction, like 3/5, this goes to 0, so this limit's 0, and so a n converges. 33. And 33 is an equals negative 1 to the n over 2 root n. Okay, so a couple of things here. First of all, let's get this negative 1. All that does, this thing, it just makes it alternate, plus and minus. Okay, so you can kind of ignore it because all it's doing is going back and forth between plus and minus. I just want to know what's happening to the limit. So well, the way to think of this, if I look at f of x equals 1 over 2 root x, the graph of that is this, something like that shape. And so what I'm doing here is the sequence is just elements of that. And then if I have a negative version of this, it looks like so. And so this sequence is bouncing back and forth between this graph. Okay, so if I just look at the absolute value and find out what that limit's doing, then I can say whether this converges or not. And so let's do the limit here. Again, goes to infinity of 1 over 2 root n. That equals 0. And so the limit as n goes to infinity of negative 1 to the n 2 root n. That also equals 0. So an converges. And 50 is an equals ln n squared over n. So first things first, you got to get used to this ln of n because we've got two n's next to each other, and this n is part of the ln and this n is not. So you have to just make sure you get everything straight here. And what you're asked to do is do the limit as n goes to infinity of ln n over n. This is squared. If it helps you, you can rewrite this in terms of x and just use continuous values instead of discrete. Write that, and now if you think this, this is infinity over infinity, so we can apply L'Hopital's rule. The L'Hopital's rule says to take the derivative of the top, take the derivative of the bottom. On the top, I get 2 ln x times 1 over x. That's the derivative of the top, and the derivative of the bottom is 1. So that's equal to limit as x goes to infinity of 2 ln x over x. Okay, now when I try to evaluate that, I get infinity over infinity again. I can do L'Hopital's rule again. So I get 2 over x from the top over 1. And then let x go to infinity, I get 2 over infinity, so that's 0. So we can conclude that this limit here converges, so therefore this one converges as well. So that's a nice little trick. You don't even have to switch over to x. I'm just doing that because you might be more comfortable with that. But you can just go ahead and do that with the n's. And again, be careful with the ln of n. So here we have an converges. Full problem here. So we start off with this limit. Just take the limit. Don't forget about your L'Hopital's rule trick of limits. Is the later message here. Okay. Number 53. 53. Okay, this is kind of a fancy one. So what they've established is the pattern that we have 1 0 and then a 1, and then 2 zeros and then a 1, and then 3 zeros and then a 1. And you can imagine that eventually we'll have a million zeros and a 1, but the bottom line is that we'll always get this 1 back. And so this here is an. It's hard to write a formula for that, but we could say that the limit as n goes to infinity of an does not exist, simply because you never get approaching anything. You're always, even if you sit on 0 for a long time, eventually you're just going to pop up to 1. So you never approach anything. You never asymptotically approaching 0 or 1. So we say this limit doesn't exist, and so an diverges. Not typical to get something like that on an exam question, but I would expect more of the limit type things on the exam. Okay, so that's enough for that section. Learn the ones that you just saw here, and make sure you're comfortable. And the big fact is the limit is Rn goes to 0. That's that gets used all the time, and also limit of 1 over n going to 0. That gets used all the time as well.